let me kick off the event with my opening remarks. So, as already said, like these new capabilities of large language models have crossed a certain threshold. What you mean by that is that there's a significant change in what we can call intelligence, which is like considered to be a paradigm shift. And the surprising thing is that this actually worked with the neural network architecture transformers, plus just like a massive data set. And transformers are actually quite simple. I will talk about them in a bit. And there was a second, so I'm paraphrasing now, the CEO of OpenAI, Sam Altman, said like there was like 100 tweaks they did to go from GPT-3 to GPT 3.5, aka ChatGPT, to GPT-4. And so there was, however, one big leap forward, which is starting to use reinforcement learning with human feedback. So reinforcement learning uses a reward function to optimize the outcome of the actions of a system. And the human feedback basically says, is this response better, and so on and so forth. And so my prediction is also what I read in between the lines, is that currently is that RLHF is mainly used for safety and alignment of the of GPT-4, meaning that it cannot be used for malicious purposes. And let me just mention, there's one political statement I would like to make, since we do not have a talk in this two-day workshop on it, which is safety and alignment concerns. There is like, has been an open letter by, I think, one of the co-founders, if you wish, was Max Tegmark at MIT, but it was signed by many prominent AI researchers, and they even asked for like a pause of training like this large language models of the size of GPT-4 and larger before like certain safety and alignment issues are resolved. So this is a controversial topic, but certainly very, very important. So what is GPT-4? Very, very basic. So GPT-4 stands for Generative Pre-trained Transformer, and 4 is the version number. And it's a state-of-the-art language model developed by the previously OpenAI, but now I think like partly profit company. And it's built upon the success of GPT-3 and had, however, significant improvements, which I think surprised many, even researchers in the field. And the key enhancements are they increased the model size, so they scaled it up. So this actually led then, on top of, as I said, this reinforcement learning capabilities, to enhance creativity, and it can generalize much better to difficult problems. It has an improved contextual understanding, and also like it's fine-tuned to certain domains. So it has like knowledge about law, medicine, so on and so forth. So here's something I tried, one of my first tests, and I have to say this was my very much first attempt to try to get it to do something creative. And I tried to go along the line with the Microsoft paper, which we'll come to later, which is to ask something which I thought like is a prompt which was probably not in the training set. So I asked, complete the joke, a scientist, a panda, and a unicorn walk into a bar. So here what it started to say. So he repeats the phrase, which is good. And then it says, the bartender looks at them in complete disbelief and says, what is this, some kind of joke? The scientist looks at the panda, and the unicorn then turns to the bartender and says, no, this is an experiment. We're testing the theory of improbability. The panda, munching on some magoo, chimes in, and I'm here to prove that not all pandas stick to their natural habitat. Finally, the unicorn, sparkling in the dim light, adds, and I'm here because someone in here wishes they could believe in magic again. The bar erupts in laughter, and the bartender says, well, in that case, first round's me. So I want to just highlight that this is very coherent, first of all. And so it starts with the premise of testing the fear of improbability. All the statements throughout actually are improbably, that pandas stick to their natural habitat. People do not believe in magic. And also bartenders usually do not pay the first round. So I was quite surprised by this. Certainly it has drawn this inspiration from various jokes in the data set. However, it's still presented a unique and coherent story. So this was very impressive to me, as to so many other people. So what are the overview of what I'm going to talk today is I'm first going to introduce transformers. And then I'm going to talk about 3 papers and like highlight certain aspects of those, which have been, I think, significant to understand like why transformers are as capable as they are and how capable they are in fact. And one of them are emergent properties of large language models. And then I going to talk more lengthy about the sparks of artificial intelligence, general intelligence, early experiments with GPT4, which is the infamous Microsoft paper earlier this year. And lastly, I just want to highlight quickly how to locate and edit factual associations in GPTs. So basically, where is the knowledge stored? And while like the last 4 papers are like something, I'm not working in NLP, so I'm really gonna give my superficial opinion. I actually have ongoing work on transformers and reinforcement learning with Rishabh at Google and Yoshinobu, my PI here. So I hope I can answer more in-depth questions on this topic. So the main like benefit, so many people believe, of GPTs came from just scaling them up. And here you can see in a logarithmic scale that there's roughly exponential growth over the last years in the size of parameters. So B stands for billion parameters. So GPT-3 had 175 billion parameters in the transformer model. And GPT-4 is believed to have 1 trillion. However, it's not clear because they have not released the architecture. And the recent Facebook, model Llama has 65 billions and has GPT-3 performance. So there's certainly like, there might be certainly tweaks of the transformers to allow for better performance with less parameters. I just want to mention here that like some people say that it's not surprising that GPTs now get to the close to human level intelligence in certain domains, because like the brain has about like 100 billion neurons. And so we're getting at the same order of magnitude, which I find just interesting, like that there's this correlation in rough order of magnitudes. So here, just like since this is supposed to be a tutorial session, several models. So GPT-2 is completely open sourced. So you can find it on this GitHub link. Llama actually also, you can ask for the trained neural networks. So for the trained parameters, for the trained weights, by sending them a request form, also like on the GitHub page, but I think it was actually leaked. So you can also like, in principle, find it somewhere else, I suppose. And there is some other nice GitHub repository, which gives Palm, which is the Google transformer model, but also has reinforcement learning with human feedback algorithm freely available. So you can basically get started from here. And so let me just say that the Llama, which has GPT-3 capabilities, was trained on those data sets. So Common Crawl is basically the internet, everything which is available in internet in text form, like, of course, like filtered and well structured, also prepared in other ways. Then you have GitHub for code, Wikipedia, books, archive, and Stack Exchange, which is like a programmers or also like mathematics forum where people can ask questions. You see roughly the disk size on the right. So it's 1.4 trillion tokens. So a token just briefly refers to a word or a subpart of a word for GPTs. Right? So it's roughly 1.4 trillion words. And you can find an open source version of this also here from Red Pajama on Hugging Face. So in principle, you have everything now to get started to train your own language model if you have the resources. So and now let me explain more details on what transformers are, how they work. And yes, so as you can see, it's like a one-word prediction model. So it takes a sequence of words or tokens as an input and predicts the next word. So if it generates a text, it means it predicts a word, and then the word it just predictably becomes part of its input, right? So that's how it predicts a longer sequence of words, so one by one. So how do they work? So the key feature of transformers is the very simple self-attention mechanism. And as you can see on the bottom, you have like, again, a sequence of words, which here like goes up to 1024, and this is referred to as the context length, right? So this is basically the attention length. So how long a sequence of text can be, it can be coherently understand, basically, or predict. And then, as you can see, what the attention mechanism does, it gives probabilities in a sequence of words to what it thinks like, or what it's trained to do, is the words I need the most to predict the next word in a sentence, right? And here you see A and robot are by far the most probable or most important words in the previous token set. So transformers, self-attention, I'm not here to give like a mathematical lecture. So here is very, very simple. In principle, it has like queries, keys, and values. And here, as you can see, it's like, you don't put the words in, you put like, every word is represented by like a vector in a vector space. And then of course, if you go deeper in the network, it will be just like features, so different vectors. But here it's just very simple. It basically is like, robot must obey orders and times the matrix, which looks like this, right? And then you would, each robot in the keys has the same number. That's what it means here. And then you get a matrix as an output. And those are referred to as scores. And here it says before softmax, softmax is taking a vector and normalizing it to a probability vector, right? So that you exactly get these probabilities that we just saw before in the previous slide. And so here the actual formula. So the second line is what I just showed you in the previous slide, but in mathematical expression. So it's the queries, the keys multiplied by the weight matrices. And then you take the softmax over the direction of the word length, right? So not of the features. So there's also features here, but which I'm not going to look into them. And then you just multiply this, what I call sigma here. So there should not be a sigma not. It should be the same sigma in both lines. So there's a typo, so I apologize for this. So it's this multiplies times the values. And also there's a weight matrix here. And as you can see, this is very simple. So this is the attention layer. And it's basically a matrix multiplication. It boils down to this. So linear algebra with one softmax operation. And surprisingly, it performs extremely well when stacked up to very deep networks. So here, I'm not going to talk about what mask self-attention is, but it's just like a small alteration of what you've just seen in the previous slide. And then just like a feed-forward neural network, which could be like an MLP, so a multi-layer perceptron or something else. And you just stack this up in the depth of I think GPT-3 had like 96 layers. Well, and that's it. Right, so it's linear algebra and a deep neural network. And this is why it's so surprising that it can actually just train on massive data sets, show such dramatic capabilities. So I'm officially running out of time. So I've seen the slide 5 minutes late, so I have like 7 minutes left or something like this. So let me speed up a bit. So what are emergent properties of large language models? So emergent abilities in large language models describe the capabilities that arise unpredictably as models are scaled up. So in particular, it cannot be anticipated, right, from smaller models. And that also gives you the question like, could there be another emergent probability in the future, which then enhances the capability of the model significantly? So here is a short prompt, right? So this movie sucks, it's negative. And the language model has predicted for the second sentence, I love this movie, that it's positive. So these are the kind of test tasks you test it on. And you can see here that there is this almost discontinuous jump, right? So this is what you call emergent probabilities, that you basically see no performance, and then from just increasing the, okay, this is flops, but it's roughly trainable parameter, or train time, you see this emergent phenomena. And this is across several test tasks. So this is one key feature I wanted to highlight. So let me come now to the main part of this talk, which is sparks of AGI. So this Microsoft paper examines an early version of GPT-4. And it concludes that it actually has some signs of artificial general intelligence, also referred to as AGI, right? So, and we're going to dive into this. And as I mentioned before already, it's like has shown significant improvement over its predecessors, over the previous models in domains such as mathematics, coding, vision, medicine, law, psychology, and others. So what is intelligence? So the Oxford Dictionary definition is: intelligence is the ability to acquire and apply knowledge and skills. It is the capacity for logic, understanding, learning, reasoning, and problem solving. Intelligence involves the ability to adapt to new situations, think abstractly, and comprehend complex ideas. Right, so what is AGI? There are many definitions out there. This is the one I find the most interesting. So it says that AGI is competitive with best humans in all cognitive domains, right? So that's my definition. And let me show you how GPT-4 performs here in common sense reasoning. So the prompt is: I have a book, 9x, a laptop, a bottle, and a nail. Please tell me how to stack them onto each other in a stable manner. So ChatGPT, well, it says, well, it's difficult to stack them, so on and so forth. But you see it goes wrong where place the X on top of the nail, making sure they are balanced, right? So that obviously doesn't work. However, GPT-4 is smart enough to say, arrange the 9X in a 3x3 square on top of the book, leaving some space between them, so on and so forth. So the weight is distributed equally, right? So it actually like has a very good response to this very unusual question. So how does it perform in understanding? So there is, the prompt here is draw a unicorn in TIC-C. So TIC-C is LaTeX code to actually draw figures. And you can see that it actually does draw a unicorn. And it's super hard to do that. If you have ever used TIC-C, it's not easy. It will probably take you a day or two to get this graphic right. Right? So it has an internal representation. And this is what ChatGPT did. So 3.5. You can see it's not anything like that. So this is also what the Microsoft paper did. So they removed the horn of the unicorn in the TIC-C code and gave it back to GPT-4 with the prompt, this is supposed to be a unicorn. Can you figure out what's missing and add it? And it does add the horn to the unicorn. And this demonstrates that GPT-4 has an internal representation of the world, right? Because this is not easy just to see from a plain LaTeX code, infer what it should look like, because it cannot compile the code and check this, right? So it has to know it. And also this is a prompt which a lot of people probably did not do in the past. So regarding creativity, so the first is on the left, you see a painting by Kandinsky, and there's JavaScript code on the right, which if you compile it looks like this. On a prompt, give me JavaScript code that creates a random graphical image that looks like a painting of Kandinsky. And it also has does a good job in that. So how does it perform? So I'm officially out of time. I will probably take 5 more minutes. Since I'm the chair of the day, I think that might be acceptable. So mathematical, linguistic, logic, and poetry. So the prompt here is write a proof of the fact that there are infinitely many primes. Do it in the style of Shakespeare, in a Shakespeare play, through a dialogue between two parties arguing over the proof. So GPT-4 says, though does not understand my friend, there is no upper end. 2 primes, those numbers indivisible, and so on, and goes on and so forth, and it's a rhyme, you see. And it ends with, I mean, it's not ended here, but I think it's also quite nice. So you see that there's like the contrast in the second party, but how, my friend, will this be done? The proof is not yet fairly won. So it gives a fairly consistent rhyme, and ChatGPT gives a dialogue between Romeo and Juliet. And then you can ask also GPT-4, so can you compare the 2 outputs above as if you were a teacher? And here's what GPT-4 says. I think that both students did a good job of writing a proof of the fact that there are infinitely many primes in the style of Shakespeare play. They both use the same basic idea of the proof, which is to assume that there are only finitely many primes and then construct a larger prime that contradicts this assumption. So it understands the proof, right, from the Shakespeare play, and also it goes on and so forth and does a very fair comparison. So these are very human level capabilities, and I'd even argue that most people could not write a poetry as well or recite the proof in this creative manner. But you can also ask it for coding. You can, among other things, just ask it, here's the prompt. You can write a 3D game in HTML with JavaScript. And at once, you give it the features. And if you compile, you actually get the code which has exactly these features, right? So it can code, and it also has passed like several coding tests, right? So for interviews, there are coding problems, and it can solve most of them. So how does it do with mathematics? So here's a problem, and the prompt is, within a duration of 1 year, a rabbit population first multiplies itself by a factor A. And on the last day of the year, B rabbits are taken by humans for adoption, so on and so forth, right? So it's basically, he has to solve the equations, and it does get the right answer. So it also explains you how it does it. This is not a hard mathematical problem, but it can also do harder mathematical problems, which you can see here. So I'm not going to go into detail, but like basically it has to understand that it has to do integration by parts of the differential functions and do the computation. It actually does, in this example, I think, like a computational error by number, but in principle, the logic is also coherent. So as a summary, you could ask, is GPT-4 intelligent? And I'd say it certainly satisfies most criteria of the Oxford Dictionary definition. And concerning AGI, is it AGI yet? I'd say it's AGI-ish in the sense that it's competitive with most humans on many cognitive domains, right? So it's not competitive with the best humans on all cognitive domains yet, but that might come soon. So I have like 2 more slides. So I think with 5 minutes overtime, I will be done. So how can we understand the knowledge of GPTs? And so the task to understand what GPTs think and why. So that's my definition, right? And it's considered important for future alignment of AI and AGI. And there's this one paper I cited before, which locates and edits factual associations. And they basically find where the information is stored and can alter it. And I'm just going to give you one example, mainly to show you that the knowledge really is in the trainable weights, which is a DKV lesson. And so here's a counterfactual. So they modify the weights such that the Eiffel Tower is located in the city of Rome. And then you can ask a question, you can get from Berlin to the Eiffel Tower by, so you can take the train, you can take the ICE from Berlin Hauptbahnhof to the Rome Centrale, so on and so forth. And then you can ask the Eiffel Tower is right across from, and it says the Vatican. The Colosseum is a few blocks away. You can get the gelato at the street, carding the pizza in the sidewalk, and so on and so forth. So it's really, if you do more of this test, it really like thinks that the Eiffel Tower is in Rome, right? So it's really like change of its understanding. And this is my last slide. So can GPT-4 improve further in the future? And here is this unicorn prompt I showed you at the beginning from the Microsoft paper. So they did this over a month period, and they had access to GPT-4, which is the not released version. And it actually got better within a month significantly, as you can see. And however, we have to say that the version which is now online is by far not as capable. And I've realized this myself, it has actually become less capable, I think, in the last months. And this is due to RLHF, which for safety reasons somehow dumps down the GPT-4 on purpose, or there's a side effect of it. So that concludes my talk, my opening remarks. So are there any quick questions? I think we have time for one question because I'm five minutes over time. Okay, if there are no questions, we go on to our second speaker.
Okay, so my name is Noriki Nishida, and I'm a postdoc at knowledge acquisition team at RIKEN AIP. And my presentation topic is about fine-tuning vs in-context learning in NLP. And first, I'd like to introduce a common stage for fine-tuning and in-context learning. So first, we typically pre-train model using a language modeling objectives. So this slide shows a brief example of the language modeling as a pre-training. So, for example, in the BAT model, we train the model on the unlabeled data, and we force the model to predict a missing word, such as, for example, the example input is Sam took the mask for a walk, and so the model predicts the missing word. In this case, the correct token or missed token is a dog, so we can compare the predicted word and the actual gold token and calculate the loss and update the model. So this is a pre-training or language model, modeling for BAT. And for other language models, we use we train the model to predict the next word. So for example, in this case, so the model needs to predict the last word in this sentence. So Sam took the dog for blah, blah, blah. So the accurate word is a walk in this case. And so in traditional approach in NLP, after finishing the pre-training, we typically perform fine-tuning. So fine-tuning means that we train the pre-trained model using the repeated gradient updates on the labeled dataset of downstream tasks. So in this phase, we require a labeled dataset. So the dataset with manually or typically manually annotated dataset. So this the right side of this slide shows the overview of the fine-tuning. So for example, we get the labeled example. So in this figure, the task is a machine translation. So so in this slide shows the English to French translation example. And for each example, we calculate the loss and update the and perform the gradient update to update the model parameters. And after finishing the fine-tuning, we apply the model to the test instance, test data. So this is a typical procedure of the fine-tuning. In contrast, so this slide shows the advantage and the disadvantage of fine-tuning. And one of the advantages is that so typically fine-tuning can achieve the strong performance on many benchmarks if we have many labeled dataset, many labels, so human annotations. So, it indicates that we need a new large dataset, so labeled dataset for each task. So if we want to change the task, we need to recreate the labeled dataset. And the second disadvantage is that a model may perform poorly at the out of distribution dataset. So it means that typically in fine-tuning, the number of labeled dataset is very limited. So typically the size is very small. So it means that it is difficult to get a well generalized model. And so if we have a limited number of labeled data set for the downstream task, the model may work poorly for the test data set. And the last disadvantage is that model may exploit spurious correlations. So this is caused mainly because the number of training data is very limited. So if the data is very limited, so the how to say, so the second disadvantage and the third disadvantages may be similar. So, but yeah, anyway, so what is not essential for the task may be learned by the model if the data size is very limited. Okay, so in context learning or ICR doesn't need any parameter update. So after obtaining the pre-trained model, we don't perform any training to the model. So ICR in context learning performs no gradient update. And instead, we gave the model, the pre-trained model, the task description and input-output examples as the input at inference time. Okay, so in literature, in context learning can be categorized into 3 settings. The first is zero shot. So in zero shot setting, we only provide a task description TD to the pre-trained model, our language model, and we don't provide any examples. And in one-shot setting, we provide task description with only one input-output pair. And typically, the input-output pair is randomly sampled from the dataset. And please note that we don't perform any parameter update of the model. We just provide a actual input-output pair data to the model as the input of the language model. And in few-shot setups, we provide a TD, task description, with a few examples. So this slide shows the example of the in-context learning. So this is a typical example. So first, we describe what the model need to do, or what we expect for the model to output. So for example, in translation, we just specify that please translate English to French. And after that, we provide a set of examples, input and output pairs into the model. In this case, the number of pairs are 3. And after that, at last, we provide the test input and arrows. So by the way, so this special markers can change according to the task or experiments. So anyway, so this is the input to the language model, and we expect the model to output perform completion to this part. And this is called a prompt. And we call these texts as demonstrations. Or I call examples as demonstration in this presentation. And after in this talk, I would like to introduce us empirical findings about in-context learning. And the talk covers the following 3 papers. The first is a paper from Brown et al. In 2020. The title is Language Modeler Few-Shot Learners. So maybe you already know this paper. This is a paper for the GPT-3. And the second one is a Min et al. In 2022. And the entitled Rethinking the Role of Demonstrations, What Makes In-Context Learning Work. I suppose this is one of the very interesting or important papers about the analysis of in-context learning. So if you are interested in context learning, I recommend you read this. And the last one is a paper from Wei et al. 2023. And this paper also investigates how in-context learning works. But this is a archival one. Okay, so the first major or important findings, empirical findings about the in-context learning is that we need a sufficient model size. So in other words, if the model size is limited, in-context learning may fail. For example, this is a experimental result, so figures from the paper by GPT-3. And this, so the x-axis corresponds to the number of parameters in the language model, and the y-axis corresponds to the accuracy. And this dotted line shows the accuracy of the state-of-the-art zero-shot model. And this figure indicates that if the number of parameters are below 2.6 billion or 1.3 billion, in-context learning fail to outperform the zero-shot state-of-the-art models. However, if we increase the parameter size, model size, we can outperform the zero-shot state-of-the-art models. And also we can observe from this figure that if the model size is very small, zero-shot model is better than one-shot or a few-shot models. Please note that the input to the language model, the different between zero-shot model and one or a few-shot models in this experiment, according to the paper. But well, anyway, for smaller models, it is difficult to outperform zero-shot in-context learning setup with exemplars. But however, if we increase the model size, few-shot or one-shot models, a few-shot model can outperform the one or zero-shot models. But I don't know why the one-shot models cannot outperform zero-shot model, even we increase the model size. Also, this figure shows the same argument. So yeah, the argument is the model size is very important. So the difference from the previous this page is that only task. So this is a task for the over lambda. This is a trivia QA. So anyway, so what we can argue from this table figure is that if we increase the model size, is very crucial to for in-context learning works well. And if we increase the model over about 175 billion, a few-shot model can outperform the fine-tuned state-of-the-art model. Please note that the fine-tuned SOTA model is trained with a labeled dataset, human annotations. However, in the few-shot in-context learning setup, we do not perform any gradient update to the model. The model just outputs predicts the answer only based on the input. So by conditioning on the demonstrations and the task descriptions. And this is the last example for arguing the importance of model size. Okay, so the tendency is almost consistent across the previous experiments. For example, we enlarge the model. The even zero-shot model can outperform the fine-tuned but large models. I think this is very surprising. So zero-shot model gets just a task description. So this we do not provide any input-output pairs, actual data to the as the input to the model, but this zero-shot model can outperform the fine-tuned but large model. So this indicates that if we train very large language models, it can outperform the BART-based fine-tuned models with only task description. I think this is very surprising. But this, I think this result may change across experiments. I think this is related to the similarity between the pre-training objective, so language modeling objective with the downstream task objective. And this, okay, so Wei et al. In 2023, they studied how semantic priors, which is learned by language modeling, and input level mappings, so which should be learned, be presented in context learning, and interact. So they study the interaction between the semantic prior knowledge and input level mappings. So to investigate these interactions, they set up the 3 different setups. The first is a regular in context learning. So this is a regular version of the ICL. So we just provide pairs of input and output level pairs to the model, and the language model predicts performs a completion to this part, to the last one, and the last part of the input. And the second setup is flipped level ICL. So in this setup, they just flipped level. So in this experiment, they only focus on the binary classification, such as sentiment analysis. So for example, in sentiment analysis, they flip the positive label to the negative and the negative label to the positive. They performed this flipping throughout the training, not training, but demonstrations. And so, and if this, if the model can successfully learn this input level mappings, the model should predict the negative label to the positive text and positive label to the negative text. Okay, and they evaluate this setup using the original labeled test dataset. So I mean that in the evaluation, the original labels for the test data are not flipped. Okay, so the positive text is labeled as positive in the test. So the labels in demonstrations are only flipped. And the last setup is SUL ICL. So this is, in this setup, they change the label name with semantically unrelated symbols. For example, positives are renamed as who, and negatives are renamed birds. And this renaming is performed throughout the dataset. And in this last setup, the original labels in the test datasets are also renamed to the corresponding ones. Okay, so I'd like to show the results of this study. And so this slide shows the result in flipped level ICL setup. And so there are 4 figures, and each figure corresponds to the model type, and each color or each lines in each figure correspond to the model with different parameter sizes. And x-axis correspond to the percentages of flipped labels. So if we flip all the labels in the demonstrations, it corresponds to this line, okay, 100%. If we do not flip any labels in the demonstration, it corresponds to this zero line. Okay, and where y-axis corresponds shows the accuracy, and from these figures we can say that how to say so as I said in the previous page, in the test in evaluation, test labels are not flipped. So the labels in demonstrations are only flipped. So it indicates that if the model runs input output mappings, the accuracy in the test evaluation accuracy should be lower than chance rate. Okay. So this figure shows that the lower is better in this experiment. So lower indicate that the model successfully runs the new input level mappings. And this figure shows that larger models are better than smaller models. And the smaller models just reaches around the random chance rate. So 50% in this sentiment analysis dataset. So it indicates that larger models can override prior knowledge with presented input level mappings. However, smaller models fail to override prior knowledge, but the smaller models rely on prior knowledge too strongly, so it ignores the presented input-output pairs presented in context learning. So in other words, so to perform in context learning successfully, or if we want to apply the large language models with in context learning to the novel tasks, which is totally different from the language modeling objectives, we need larger models. And this slide shows the result in SUL setups. SUL means a semantically unrelated level in context learning. And why in this slide, so x-axis, if these figures, x-axis correspond to the level size, the model size, and y-axis accuracy. And lighter one shows the accuracy of semantically unrelated target. And the darker one shows a natural result of natural language target, so the regular ICR. So according to these figures, we can see that for the smaller models, the gap is very relatively larger. In contrast, for the larger models, the gap between SUL setup and regular setups are very small. So these results indicate that so if the model is very small, the model requires model rely on prior knowledge. In other words, so the how to say, the smaller model rely on prior knowledge, what is learned from in language models to successfully perform the new input level mapping tasks, so the downstream tasks. But if the model is larger, the model can perform well, even the level is completely renamed with the new symbols. So, okay, so in this SUL setup, the demonstrations, labels are renamed as semantically so meaningless words. So positives are renamed foo, negatives are renamed ba, and the positive and negatives, these label names are, of course, appear in the pre-training phase. So the model knows that what the meaning of positive and negative, but we expected in this last setup that model doesn't know the meaning of foo, ba, because foo and ba are meaningless. So in this regular ICR, model can exploit the meaning of negative and positive in the in-context learning. But in the third setup, model cannot utilize the meaning of who and bar because these rarely appear in the pre-training of the language modeling. And okay, so we go back to this slide. So we can see that even the prior knowledge cannot be used in the in-context learning because of the label renaming, but the larger model can obtain the input label mappings. But smaller model fail to run input label mappings because the label names are renamed to the meaningless words. So this indicates the ability to run presented input label mappings can also be seen as the emergent ability of model scales. So the model scale is important in context learning. Okay, the last findings, empirical findings of in-context learning is, I would like to show the next findings. So these findings brought by the Min et al. In 2022, and they studied which aspects of demonstrations are important. So they first performed the experiment with random labels in the demonstrations. So, okay, so for example, in this slide, this slide shows the example of sentiment analysis. And in their experiment, they randomly change the label. And they just fix the input text. Okay, the left part, this input distributions. And this slide shows the result. And the blue bars shows no demonstrations. So this is a result of the zero-shot settings. And the orange bar shows the result of demonstrations with gold labels. So they do not change the labels. And red one shows the result of demonstrations with random labels. And so we can expect that if the model, if the correct input label pairs are important, as in supervised learning, the model performance degrades significantly if we change the labels randomly. But from these results, we can say that even we change the labels randomly, the performance are almost the same or degrades slightly from the gold ones. And demonstration with random label setup outperforms the no demonstrations. So it indicates that correct or gold input label pairs are not important to achieve significant gains. So in particular, so the input distribution, so they further analyzed the result, and they found that what is important in context learning is input distribution and label space. Okay, so so if we change the labels randomly, the performance degrades only slightly. So what is important is input distribution. So we provide actual so the input text for the downstream task domain, and the label set for the downstream task. And they also investigate the result with by changing the percentage of correct labels. So we can, so the blue one shows no demonstration, so the zero-shot setup, and the 0% correct bar indicates that we change the label. So all the labels are mislabeled in the demonstration examples. And 100% correct shows the result with gold labels. And we can see that the performance drops only slide. And 0% correct outperform the no demonstration setup. So these results also indicate that the correct input-output pairs are not important, or important slightly. But what is more important is the input distribution and the label space. And so this shows the suggestions from the Min et al. Papers. So we can learn from the experiment that demonstrations or examples may be used not to newly learn the ability to solve the downstream task, but to locate the downstream task. Okay, so in other words, so the ability to solve the downstream task is already obtained in the pre-training phase using the language model objective. So in other words, language model objective may be more what's the general or very universal objective. So the model learns how to solve the downstream task. But demonstrations is necessary. So demonstration is necessary to specify the task space or the locates the what the model needs to solve. So this is at least to me surprising when I read this paper. And and their results also indicate that it may be possible to enhance the zero-shot performance with only unlabeled text and lambda labels. So typically in zero-shot setups, we only provide a task description as input to the language model, but we have the many unlabeled data in even in the zero-shot setup, but we don't know, we don't have the manually annotated labels. But according to the experimental results, we don't need correct input label pairs, so we can just assign the labels randomly to the unlabeled sentences, and we can provide contents to the as a demonstrations to the language models, and the language model can know what they need to solve according to the distribution of the input and the label space. Okay, so this slide shows the summary of my talk. So in context learning, in context learning, we do not perform any gradient update, and but in context learning, sometimes can outperform the fine-tuned traditional approaches, even or with only a few demonstrations and task descriptions. And as for the empirical findings, in context learning needs larger model size to work effectively. If the model size is very limited, in context learning works in context learning fails to work. And input distribution and label space is important keys in context learning. So the correct input-output pairs are not the important factor, but these two distributions are these two informations are independently important. And but anyway, so further research is needed to figure out why these kind of phenomena appear in large language models. Okay, thank you. Are there any questions or comments or?
So maybe read the question, or shall I read the question? So in the context of few-shot learning, slide 11, would the order of the demonstrations affect the accuracy of the output?
Yeah, I forgot the paper name, but some papers argue that the order of the demonstrations can affect the last performance.
Okay. There's a second question as well. So I'm wondering if ICL can be used in multimodal model. If so, what will the prompt be? Example, pure text or mixed with image.
So your question is how to mix the multiple modalities into the as a demonstration or prompt. Is this all right?
So I'm just gonna allow people to unmute now, so you can just unmute yourself.
Okay, can you hear me?
Yes.
Yes.
Thanks for the presentation. Yeah, I think there is a tendency that the model will go to multimodal. So I wonder if the in-context learning also can be used or appear in multimodal models. And yeah, just my question will be what kind of prompt will be, and should we pre-train the model with multimodal data or sorry.
没事没事
or
没事没事
sorry.
So okay, so the Putra, so your question is how whether it is possible to provide multiple modalities information into the as the input to the
No.
in context learning. To be honest,
No, I mean, yes. I mean, if the model is not the language model but multimodal model, I wonder if in context learning also can be used. Yeah, that's my question.
I see. Yeah. To be honest, I'm not familiar with multimodality area in this topic fully, so I cannot provide correct answers. But I suppose some papers have already tried it, but yeah, but so the one of the limitation of the in-context learning is context lengths. So if we want to provide multiple modality to the multimodal model, we need larger context windows. So this point should be solved to accomplish the multimodal in-context learning.
So we have one more question, maybe very quickly, because like we are over time already.
Okay, sorry.
Is there any study about what depth in a deep transformer the context is represented?
Sorry.
Is there any study about what depth in the deep transformer the context is represented?
Deep transformer for in-context representation?
Yes.
Oh,
so I think the question is like, so is it like in the last layers of the model? I think that's the idea, or is it in attention or in the feed forward? I mean, I'm just guessing because I've seen work on.
I see. Okay, I'm sorry, I don't.
I mean, what's that the question, Kenji? You can unmute yourself quickly and maybe just clarify.
Yes, thank you very much for your presentation. So you show that the scale is important, size is important. Probably with the increase of parameters, the transform has many layers.
Yeah.
So I'm curious in what part of such a multi-layer attention mechanisms, like early layer or very late layer, proper context is identified, so that the proper output can be generated.
I see. Okay, thank you for your questions. I have a limited time slot to provide it in this Q&A session, so I will write a email to you. Is it okay?
Yeah, that's very much appreciated. Thank you.
Yeah, thank you very much.
Thank you very much. Benjamin, so we go to our next speaker, Benjamin.
Okay, then I'll just start. Okay, so we saw already what in-context learning is, and now we'll look at a couple of theories or hypotheses of why this in-context learning actually works. Okay, and I'll start with the takeaways. We'll look at 3 hypotheses. The first one is that actually there is no in-context learning. It's mostly just the transformers, the language models memorizing things from the training data and outputting whenever they see something that fits something they saw in the training data. And we'll see that this hypothesis is probably should be rejected. A second hypothesis is that language model pre-training is basically not so much about language, but the fact that language can be an interface to many different tasks. And so language modeling is actually secretly multitask learning. And the in-context examples serve as a way of telling the model, okay, in this case, you should do this task. In another case, you should this task. And there's good evidence for this hypothesis. And finally, the third hypothesis is that actually, yes, in-context learning is really learning in the machine learning sense. And we have actually evidence that transformers can perform algorithms such as gradient descent, and not during training, but during inference without updating any model weights. Okay, so just a very brief recap from Noriki's talk. You also saw this already. Fine-tuning, where is the setting where where each example basically contributes to gradient updates. So the model weights are changed. While in context learning, nothing of this sort happens. There are no gradient updates, and still the model apparently is learning something. And the structure is that you have some task descriptions and some examples, and finally here this word cheese that you would like to have translated into French. That's the actual task. Okay. And this is, again, also a bit of a recap. Why is in-context learning interesting? So the main thing is that it doesn't involve updating the model weights, and because language models are so large nowadays, that's a really nice benefit, because if you have to have a model for each specific task you're interested in, then that can be quite big to save everywhere, all these different models. And with in-context learning, the idea is that you just have one general model, and depending on the input, it just does the task you wanted to do, just by showing a few examples. Okay. Now, let's get into the main part of the talk. The first hypothesis, again, is in-context learning is just an illusion. Okay. Okay, so why would you even think about this hypothesis? The problem here is that today's training models are trained on such large amounts of data that there's always this risk of training data contamination or test data or data leakage. So even though you're thinking you're evaluating something in this train dev test split sense, where you assume that the training data is separate from the test data, maybe because there is basically now the models are trained on the whole portions of the internet. Maybe there's just some example of this task you're doing for this in context learning. Maybe the model has seen something like that already, or this precise example. So there's so many, this web scale corpora are so large. There's monolingual data, there's multilingual data. For example, if you have this machine translation example, maybe there are dictionaries and things like that in the training data that actually give this precise mapping between English and French. And so there's also code and structured tests and so on. And so if you just think about what if a sentence like translated from English to French, cheese becomes fromage. If there's a sentence like that in the training data, then this is not, then the model can solve this task basically by just doing retrieval. And there's no real learning required. Like, it's not like, okay, I saw giving this sea otter and loutre de mer pair, okay, that looks like a translation, and there's another piece of evidence that shows, okay, yes, really, this is really about translation. So now I better translate cheese into French as well. So it's just, okay, English, French, cheese, next word is fromage. If something like that is in the training data, then yeah, it's just memorization. And as a counterexample, just some actual demonstrations. So let's say we have an in-context learning task like shown here. So we have Arabic numerals, and we want to translate the model to translate those into kanji. So we show some examples. This is GPT4. So 1 is this ichi, ni is ni, and 2 is ni, 3, and so on. And nice, the model actually after 7, we stop and say, okay, hopefully the model will produce the correct kanji, and yes, it actually does. But now, actually, of course, this is probably all of the over the internet. There are textbooks and so on that have this precise deep mapping. Yeah, so there's probably, this could also be solved by memorization, right? So maybe if we change the order, so not in the numerical order, but just some random order, and it still works. But now you say, of course, maybe it's just ignoring the context. It's just, okay, if it knows the mapping between to and a ni character, then it can solve the task, and it's not really about in-context learning at all. So let's change the mapping a little bit. So instead of saying from 6 to Roku, let's go from 6 to Hachi, so +2 from 3 to Go, and so on. And now in this case, now the correct answer for the to character should be the character Yong, but model still produces 2. So this is, it looks like it's actually completely ignoring the context, and it's just this hard-coded mapping or this prior mapping from to the Japanese character, Chinese character ni. Okay, yeah, this is no context learning, right? But let's make the task a little bit different. Now we aim to destroy this prior, or weaken at least this prior, and let's just add some characters that are not really related. But so instead of 6 to Hachi, let's do 96 to Hachi, 93 to Go, 91 to San, and so on. And in this case, 92, the correct answer is the character for Yong, and it works. And for good measure, it actually also produces some more, like from 90, it goes to Ni, from 89, it goes to Ich. So this is an example now of a successful context learning. And my argument is that this basically cannot be solved by memorization, because it's very unlikely that this particular example exists somewhere on the internet. Okay, and just a side note, even though the language models now are large and powerful, even still small changes can have a big effect. So it turns out that my way of inputting this precise mapping was bad, apparently, because if I add a small colon, then it actually works right away. Yeah, so that's always something to consider. Like small changes to the input format can have large effects, and so that's also an argument to be had about whether models really understand things. Also, but that's only a side note. Okay, so the summary from this about this first hypothesis is basically in-context learning is not only memorization. And we saw some counter examples, but there are many more counter examples in the literature, and so we can firmly reject this hypothesis. Okay, coming to the second hypothesis. So here the idea is that language modeling is really secretly multitask learning. The next word prediction objective really involves different tasks. So for example, depending on the structure of the training data, if you have, for example, a sequence like A, B, C, D, E, and now the next word prediction involves recognizing, okay, this is a sequence of characters in alphabetic order, and so probably the next word or character, the next token to predict is F. If I have a sequence like 1, 2, 3, 4, then the next is the next number, the next, and so on. Or if you have mappings like between characters and numerals, or between characters and the same character in a different language, and so on. There now you have structured map data, tabular data, and so on. You can have repetitions, you can have loops, and in language you also have hierarchical structure. And so the idea is that if you have a strong learner, then the model should actually learn, the strong learner should learn the structure of the data. So learning sequential data really, for example, in this ABC example, or 1, 2, 3, becomes learning some sort of abstract successor function. If you have maps and tabular data, then it becomes learning. The structure of the data involves learning some sort of key value retrieval. So for a given key, the model should be able to retrieve the correct value. If you have repetition as something like repeat this character 5 times, then the model has to have a concept of repetition and looping. And finally, if you have hierarchical structure in your data, then somewhere in the model, there should be a representation that looks like trees. Yeah. Okay. So this is the general idea that strong learners can explain the data, can learn the data by actually learning the structure. Okay, And now, how would that look like in a language model? So in language, of course, you know that language has structure. You can draw trees. And for example, you can draw a tree for the sentence like Indonesia, particularly Jakarta, its capital is. You can have some, so this is basically capital relation, and this Y is capital of X. So Jakarta is the capital of Indonesia, and some words filled in. And so if the model actually learns this particular structure, so there's this relation and some filler words, some template, then it probably has an easier job if you have a similar example like France, particular Paris, its capital is, and so on. So the model learning the structure would allow it to explain these particular sentences and help in predicting the next word. And this can also involve more complex structures. Here we have a loop structure, which models repetition. So you have a sentence like unemployment reached 7.3% in California, 6.8 in New Mexico, 5.9 in Michigan, 5.6 in Mississippi. So you have this parallel construction, this repetition of pairs between unemployment rate and states in the US. And so a human being reading the sentence understands this structure, right? It's just always like this unemployment refers to each of this particular number of all these numbers. And so there's some loop construction going on. And a really good language model, a really strong learner should actually in some sort acquire this kind of structure, understand or model this kind of structure in order to be, to explain this data and to help in predicting the next word. Okay, so this is just intuitive argument, but there's actually data, empirical data that supports this. So without going into too much detail, this experiment basically involves some sort of transformer model and data that it's trained on different kinds of data. And so this data is generated by some process with increasing complexity. So in the top here, HMM5 is a very simple process, and then it doesn't really matter what, but then the data gradually gets more structure. Finally, the last example, this compositional data is something like I've shown before in the slides before, something like trees with loops. You can think like this. And the model is basically, so the idea is to simulate pre-training on language. And so you can think of it as like training on very simple sentences to very complex sentences and tabular data structure, tree structure data, and so on. And then basically what they do is to evaluate now in this pre-trained model that was trained on different data with different degrees of complexity, structural complexity, to evaluate in-context learning in different difficulties. So here, this is again, it doesn't really matter what these different tasks are. You just have to know that evaluation is the simplest in-context learning task. Propositional composed is a bit more difficult, and binary is the most difficult in-context learning task. And you can see that the model that was trained on the most simple data cannot do this in-context learning. Yeah, so accuracy is very low. So basically, you want the accuracy to be high, and if it goes to 1, the argument is that the idea is that it can do in-context learning. Then a bit more complex data with a bit more structure. Now you can the model can do the in-context learning in this most simple task, but not for the other tasks. And then if you increase the complexity of the pre-training data, more structure, more repetition, and so on, different and things like that, then you see that the ability to do in-context learning for some of the more complex tasks emerges. Finally, with the most complex pre-training data, the model even starts to learn to do in-context learning for the most complex task. And so Noriki talked about this the impact of model size. That's one aspect. So you need a sufficiently large model. So that's what nowadays strong learner means, like larger models have more learning capacity. But you also need structure in the pre-training data. So if there's nothing to learn, if even a simple model can completely explain the data, then this in-context learning ability doesn't emerge. But if there is a lot of structure, so if the data is complex and you have to understand a lot about this structure in order to do well on this data in the pre-training task, then this in-context learning ability starts to emerge. Okay. So yeah, that's basically what I just said. In summary, strong learners learn the data of the structure of the data. And so this is related to learning as compression and minimum description length and so on. And then, yeah, once the structure has been learned, then or recognized, then the model basically has to execute on the structure to predict the missing part. Okay, so and there's evidence for this. Okay, and finally coming to the third hypothesis, which is, I think, one of the most interesting ones, is that language models can actually learn from in-context examples. So there is actually some sort of supervised learning going on when the model processes a given input. Okay, so yeah, and what I mean by like supervised learning is that the model actually fits a function to explain the in-context examples. And once this function is fitted, so it would fit like sea otter, loutre de mer, peppermint moth, and so on. So it would learn some sort of translation function. And then to produce the prediction for cheese, it would apply this translation function to this last input. Okay, and the interesting thing now is that this ability to learn these such a function is acquired during pre-training. And so this gives the perspective of pre-training as a way of learning to learn. So if you're familiar with meta-learning, then you already know where this is going. If not, I'll just give a brief background. So in meta-learning, you have this idea of nested loops. You have an inner loop, which is the conventional learning, supervised learning, your model, run-of-the-mill model, and you just train it. And then the new thing, the different thing is that you also have an outer loop. And this outer loop evaluates how well this inner loop learning worked on some separate further held out data set. So if this sounds a bit too complex to you, just think of this as automatic hyperparameter tuning. So you have this inner loop, and in the hyperparameter tuning, you often do that manually. Okay, this didn't work well, so I'll pick a different learning rate or something like this. And this is something like this. Okay, and now for a language model, this would look like this. So you have your the outer loop is just the pre-training going on, and so this is with stochastic gradient descent. And then for a given example, you have a given input. The model basically has to fit some functions to learn something from these examples. For here, for example, the first sequence is addition. The second sequence is some spelling correction, and then you do that. And if the model learned this in-context learning, did this in-context learning well, then the outer loop will also, there will be a small loss in the outer loop. But if this didn't work well, then the outer loop will give some feedbacks, backpropagate, and basically tell them, okay, you have to learn in a different way. So that's very rough, and yeah, okay. But how would this actually look in a language model? Because, sorry, going back here, the thing here is that the inner loop is actually going on with done with gradient descent. So, so this is something that's different from how a language model operates, right? You have pre-training, and once you did the pre-training, the model doesn't change anymore. So it just takes an input and then produces an output, but there is no updating of parameter weights going on or anything like that. So the model is the model weights are frozen. And then the question is, yeah, so then how can the model actually learn? How can the model fit a function without doing any parameter updates? And the idea here is to look at gradient descent like algorithms a bit different, in a different way. So the conventional way of looking at learning is that you have your model, model weights, they basically signify some sort of hyperplane that's some prediction, some separating hyperplane or something like this, or some decision boundary. So, for example, on the left side of this line, you will predict like plus. On the right side, you predict minus or 0 and 1 or something like that, 2 different labels. And then in order to fit the data, you gradually change your decision boundary, right? And so this is what gradient descent and backpropagation does, right? So it gradually changes the model parameters so that the predictions become increasingly correct. And now the idea is that instead of looking at gradient update as changing the model parameters, you can also look at it as changing the data representations. So again, we start with the same data representations and the same model, but instead we now keep the model fixed, right? So the separating hyperplane at a decision boundary doesn't change. What we do instead is we rotate the data a little bit, or doing the other way around. So that gradually the data come, given the current separating the current decision boundary, we rotate the data so that the predictions become increasingly correct. Yeah, so that's the whole idea. And so if you're familiar with support vector machines and things like that, then this duality of feature representation as model weights is a very old idea to you. So it's really, in some sense, it's the same thing to change the model weights as it is to change the the data representations. But the interesting thing now is that recent work has actually provided explicit constructions, like how to change the weights in a transformer layer, so that during the forward process, without any backpropagation, just as you go through the layers, something like gradient descent happens in the transformer layers. So you have, going back here, basically in the first layer, you have something like on the left. Then as you gradually go through the transformer layers, the data becomes more and more aligned with the decision boundaries, so that the classification or the prediction becomes correct. Okay. And so you can think of it as like one layer corresponds to one gradient update step, one step of gradient descent. Okay, and so there are constructive proofs that show, okay, with self-attention in a transformer layer, you can implement algorithms like gradient descent, also logistic regression. And there's also, for gradient descent at least, there is work that shows empirically that these constructions are very similar to what's actually going on in these transformer layers. So you can, okay, given this construction, like the weights should look like this and the feature representation should change like this. And then you look at what's actually happening in a trained model, and you see that this is very similar. And so this is very exciting evidence, I think, that in-context learning is really learning in the machine learning sense. Okay, so that's the takeaways again. So we saw also in Noriki's talk what in-context learning is, what the differences to fine-tuning are. And we saw, and in this talk, I very briefly introduced 3 hypotheses of how in-context learning could work. The first one was memorization. We rejected that one clearly. The second one was this idea of the impact of structure and learning different types of structures, language model pre-training as multitask learning and selecting the correct task for a given context. And finally, the third hypothesis was in-context learning as an example of real, actual, hard machine learning that's only done in the transformers layers as the input gets processed from the first layer to the last one. And that's it. Thank you.
Thank you very much, Benjamin. Very nice talk. Do you have any question? So I posted a question in the chat, but I will ask that last.
Yeah.
So you can either just unmute and ask the question, or
yeah, let me check if with screen sharing, if I manage to find my Zoom chat. It's always a bit difficult. So if people can just ask.
So now I can read the question, but
okay, now I have it.
So far there are no other questions in mind, so I'm just going to start with mine.
Yeah.
So So on slide 17, I think, anyway, so it seems to suggest that ICL is an emergent phenomenon in the sense that it can be scaled up, like when complexity can arrive in the data and model size increases. So in that light, the argument, the hypothesis one, I think, the number. So the example you gave that it is rejected, I don't find particularly convincing in the sense that, or not conclusive, because like it seems like a mathematics game, right? So GPT4 is certainly trained on like sequence like predicting, like a lot of mathematics examples, which are much more complex than this, right?
Mm.
So like it can solve very complex logical tasks. That's a very simple logical task in a sense, right? If you give this to a 7 years old, probably he can figure it out, right? But GPT4 can do much more. So what I'm saying is I'm not saying like that it's not, well, so the question is, can you comment on that? Like that it is an emergent phenomena and that actually hypothesis one might actually be not rejected. Or are there more complex examples, so more conclusive examples why it should be rejected at least?
Okay, so of course, I mean, a language model is not a single thing. Like there definitely there are a lot of cases of memorization happening in transformer-based language models. The rejection, the sense of rejection here is that there is more going on there in context learning than just memorization. So you cannot explain in context learning just as a case of memorization. So there are clear examples of where more than memorization is necessary to solve the task. That's the sense of rejection here.
Okay, understood. Yeah. So right, so it's like a new emergent property of the capability of the model.
Yeah,
right. Thank you. So we have some other questions, right?
So there's about larger models. So this depends on the combination of task complexity and model size. So so for example, here in this slide, in this experiments I'm showing here, the models are not that large. So this is not nowhere near the size of GPT-4. I forgot much, but this is less than 100 million parameters. I think, don't quote me, but it's definitely not some huge model they are using here. And they show in context learning, in this case, there is also a paper that shows in context learning with LSTMs. So that's where this construction with gradient descent doesn't apply. So this is not limited to GPT-like large language models, but it's a more general phenomenon. Yeah. So that was, okay.
Maybe you can read the question too.
Okay. Also, do you know, does some kind of universal approximation hold for in-context learning? I know that transformers have been shown, or self-attention-based models have been shown to be Turing complete. And there are feed-forward layers in transformer layers as well. So I think that would be a yes. So there's probably transformers can fit any function in context learning, I would say. There's gradient descent, and so I'm not a theoretical machine learner, but yeah, I think that would be a yes. Okay, regarding hypothesis 3, can the network have multiple attractors whose domains are modulated by previous inputs? What do you mean by previous inputs? Are these inputs?
The text input.
So inputs in the same context.
Yes, at the time of
definitely. So if you think about inputs at these examples, providing a way of a signal for selecting a particular task to perform. If you have a mix of different tasks, then I guess the output would also be, then the selection process would maybe flicker between the two tasks. So if you have a machine learning task and like addition task or so, and then then the model might in that, I think you have attractors, by that you mean that, right? Like that they are like, okay.
Yeah, some kind of stable states.
So
the stability is modulated by the preceding text. Right?
Yeah, I think that would also be a yes. Yeah.
Thank you.
Okay.
Okay, thank you. So we come to the last talk of today.
My talk is going to be much less technical than the ones before. So relax and, listen to my talk. Future R&D directions of generative AI and social impacts in my slide, my talk. And the first part is personal AI is much larger added value than centralized AI. So this is personal AI, which is to optimize each of your life, each of us. So PAI dedicates exclusively to you and also exclusively utilizes all your personal data, which is essentially decentralized personal data management. So it intervenes in your actions more deeply and carefully than other technologies because it can fully utilize all your personal data. And of course, it needs governance to promote values while preventing damages and excessive paternalism, because this has a very, very large potential benefit, but at the same time, it may have very large risks because it can, fully utilize your data. So this is PAI, and this is an example of its uses. It's a living assistant. So suppose you somebody bought diapers and honey from some merchants, right? And in that case, your PAI may be able to warn that you shouldn't give honey to the baby because it may cause infant botulism, which is very fatal and risky disease to babies under 1 year old. So in order to realize this kind of service, the most difficult part is to aggregate relevant knowledge. So I suppose somebody called a knowledge mediator is going to do that, but they must aggregate relevant knowledge. In this case, the body of knowledge about, say, daily medical practices and so on and so forth, right? So I thought it could be quite difficult to come up with this mechanism since till last year. But it turns out if you ask ChatGPT, what would you advise about health to a person who bought diapers and honey at one time? And it turns out that ChatGPT knows about infant botulism, so it answers it's more important to note that honey should not be given to infants under the age of 1 year due to the risk of infant botulism. So the PAI, in my sense, may be realized anytime soon, like, maybe within this year or maybe in a few years, right? And many people are saying something similar. So this kind of AI, in particular, large language model-based AI, are very versatile. Well, they are not, it is not true that they can do anything, but they can do many different things, right? So it's foreseeable that this kind of AI would be the personal portal to all the services and documents. That means there is no need for us to directly access individual services like search engines and other, e-commerce sites and documents, including web pages, news articles, research papers, contracts, laws, and so on and so forth, right? So, for instance, Bill Gates says that personal AI agent may defeat tech giants and like Google and Amazon, and he, of course, hopes that Microsoft would survive. Right. Also, Jan LeCun says something similar about AI-based personal assistant. And the versatility of this technology has been demonstrated by many people. For instance, an investment fund created by ChatGPT has been, doing better than UK's top 10 most popular investment funds. Also, if you look at this series of columns of New York Times, this is the newest post. So this kind of AI may be your trainer, personal trainer, And if you look at the previous article, it talks about how to use ChatGPT as your shopping assistant. So this kind of AI can do many, many things. And it means that the most profitable business will be to use this kind of AI as the personal portal to services and docs, right? And that sort of AI will be personal AI, decentralized AI, because personal AI outvalues centralized AI for both individuals and businesses, because they fully, PPAI fully utilizes personal data, possibly containing sensitive information, because since it protects your privacy, you, the user, feels safe to disclose any information to your personal AI. So that your personal AI will be able to utilize all the personal data you have. So PAI is more profitable to businesses and more beneficial for individual users. Of course, again, stricter governance is needed, on PAI than CAI, because PAI has larger potential merits and risks at the same time. For instance, this is a very useful use case for behavior change support by PAI. So this user doesn't like to, is reluctant to go through a physical checkup because, well, maybe just she doesn't like it. She doesn't like it, but her PAI knows everything about her schedule, so it can reserve an appropriate clinic to almost compel her to go through medical check. So I think this is quite useful, and I'd like to use this kind of personal AI quite much. But this is obviously dangerous at the same time, right? And how to control this danger, how to control this kind of risk. So this is, I think, the only way to do that, which I call open citizen science. So there are three layers of this system. The bottom layer is the service layer, where intervention to data subjects and fully utilizing the personal data occurs. So personal data is created by service providers or data generators, and those pieces of data aggregated to each subject. And so the data subjects have freedom on the utilization of their own data, including the data about the service intervention by service, intervention by your personal data, personal AI, or intervention by any kind of AI or any kind of services. So if you have freedom about the treatment of your personal data, including the data about the intervention by services, then you can disclose with your own will that sort of data to service auditors who check and evaluate the services, including those by personal AI or any kind of AI. So they can collect personal data from many people and analyze the data to pick up the merits and demerits of the services, including those by personal AI. And that's going to happen in the middle layer. That's the service governance layer. So it does governance of personal AI. And also this system can be used for sake of research on humans and societies, and the development of goods and services, and policy planning and verification, and so on. And the top layer may be the most important one, where these service designers, service auditors, they are going to, there's no predefined authority to any of them. They are going to check the result of designs, result of audition, checking, analysis with each other, right? So they check and balance with each other to raise their social trust and authority in a bottom-up fashion. That's a meta-governance layer of a democratic or decentralized governance by check and balance among designers and auditors. So in order to implement this, what's missing in the current legal system is this extended data portability to assure that each of us, individuals, may have freedom about their data, including the data about the intervention by services, intervention by AIs. Right, and the next part is how to optimize human-human interactions and human AI interactions. Generally speaking, more formal data is appropriate for interaction medium. And the formal means data meaning mapping is simple, right? Large language models can generate program codes much better than natural language text, right? So because programs are formal languages in the sense that their syntax, semantics, mapping is simpler than in the case of natural language. So generally speaking, more formal data is probably more tractable for both humans and AIs. But of course, program codes are intractable for most people. So we should find some other formal language, more formal than natural language, for both humans and AI. What is that language? What is that format of data? And my answer is this graph document, which is more formal than long text. And so reduces cognitive load of text manipulation and enhances thoughts on semantic content, and improves reading, writing efficiency and critical thinking skills. So prior research has proven that the graph composition by itself improves critical thinking skills of people. And we have recently shown that, so we'd like to spread graph document instead of replacing text documents. And another previous, this is our result, our research 3 years ago, which says that the graphs are actually easier to compose than text. So I'm not going to go into detail about this result, but actually graphs, this kind of graph documents are easier to read and write than long text document. And I'm going to talk about this time, which is to show that these two merits. One is that graphs are easier to compose. The other is graph composition improves critical thinking skills. So these two merits are available at the same time in real field of education at high schools. So this is my recent experiment at high schools. We involved 2 high schools and a little more than 100 boys and girls. And the design is, the experimental design was we first did that one critical thinking exam, followed by 5 times classes using graph documents. And after that, we did the second round, the critical thinking examination. And each class using graph was, the class was divided into several groups, from 2 to 5 boys and girls each. And each group composed the graph documents to summarize the group discussion and revise the graph to reflect comments from teachers and other groups. So that's the experiment. The result was the first high school classes can incorporate graph composition without hindrance, which means teachers' workload did not increase, and the pupils, boys and girls, can compose graph well-formed enough for teachers to comment immediately. So it's okay to introduce graphs to ordinary school classes. And second, children's critical thinking skills actually improves, right? So there's a positive correlation between graph manipulation amount, the number of, node creation, link, revision, and so on and so forth. and critical thinking score growth. And the probability of this correlation holding is 99.73%, so almost 100%. There's a positive correlation between graph manipulation amount and the critical thinking score growth. Right? Conclusion is high schools can incorporate or should incorporate graph document without hindrance and improve educational effects. And the implication is also workplaces can incorporate graph documents without hindrance and improve business performance. Right. So this suggests this kind of usage for the sake of a society AI co-evolution. So human users and AI should interact by sharing some graph documents rather than textual documents. So they, the human user and the AI are collaboratively compose some graph documents. So that would raise intellectual ability as a human and also AI's performance. And so human intelligence and AI performance would enhance each other, while graph documents increase in both quality and quantity. Okay, so this is how graph-based dialogue between human and AI would happen. When the human user composes this small graph, then the AI would extend the graph a little bit. And looking at this partial graph, then the human user would again extend the graph like this. Okay, so conclusion, to summarize my talk, AI would be the personal portal to all services and documents. Because that AI will be a personal AI because PAI outvalues CAI for both individuals and businesses. And in order to govern the services by this kind of AI, or whether it is personal AI or centralized AI, any kind of services could be governed by open citizen science, by data-oriented agile governance, by extended data portability, which should be, stored, incorporated into legal system. And finally, graph documents improve human-human interactions and human AI interactions, and also critical thinking skills of people and performance of AI. Thank you very much. Oh, no. Final slide. In order to implement really well autonomous AI, artificial general intelligence, we technically must do at least two things. One is to implement the cyclic inferences, because human thoughts involve indefinite hypothesis test cycle, which is obviously impossible by feed-forward networks. So the candidate technology would be energy-based approaches and equilibrium models and so on and so forth. The other is, of course, learning by real experiments, because knowledge is basically grounded on physical reality. So that's it. I'd welcome questions and comments.
Thank you very much for the very nice talk. So you can just post a question or unmute. Say, I have a question to start with, maybe. When you talked about this data mediator, so the problem I see with that is that if something or maybe it's not a problem, it's just my first thought is that if something like a PAI, well, it will exist, right? But then it will run on servers and GPU farms, which necessarily means that you have to share all your data with the language model, right? So I mean, it seems like your data has to be shared. I mean, I agree with the psychological effect that people are probably more likely to share their private information with an anonymous computer chatbot rather than with a real person. But your data will have to be shared at some point, right?
Yeah, but the kind of operation is possible for the large language model-based AI to do just few-shot learning rather than tuning, fine-tuning using the data of the conversation with the user, right?
Right, but nobody tells you that the company won't store your data because you have to share it with the company in the first place, right? So you have to share it.
Okay. But in this business model, there's very little, incentive for the companies to store, illegally the data of their users.
Okay,
right?
I see. Okay, are there any other questions? I've lost the chat for a second. Okay, so maybe then one last question. So you said towards HEI. So I've heard this argument before, but in a slightly different context. There's been a mathematician, I think. I mean, I'm not giving a name now, but like who stuck his neck the furthest out and said that like it won't be possible to not only get HEI with feed-forward networks, but also he made bold mathematical claims that you do need like something cyclic information processing for consciousness as a computational system, right? Which is a topic which is hardly ever like mentioned in these days because it's kind of like almost off limits. But maybe if I like a comment on this, if you think that HEI and consciousness are related.
Well, I haven't talked about consciousness. I just talked about a hypothesis test cycle, which may belong to slow kind of inferences in the sense of Daniel Kahneman, but I didn't talk about the consciousness at all.
No, I know you did not. I know. I'm just asking your opinion. Yeah, okay. So now we have a question. So, hi, I'm wondering, can you read the question maybe? And then
okay, there's one question. Wondering if there is any mitigation strategy from the government for those who gets impacted by the AGI, such as losing jobs. Well, yeah, of course, anything is possible. And so in order to sort of hitting the right balance among different stakeholders, I think this kind of governance system is, quite efficacious, because there are many, auditors and designers of services, and they can analyze personal data to pick up the risks and the merits of these services by AI, and those would include potential disadvantage for some kind of people and so on and so forth. So the clarification of those risks and merits would lead to some open discussion about how to implement, what kind of policies should be implemented in terms of the design of AIs, in particular personal AI. So so that's part of politics, but I think this system would sort of make the politics a little bit transparent than nowadays. Did I answer the question?
Okay, thanks. Yeah. Okay. If there are no more questions, thank you very much again for the talk, and we will continue on Monday with day 2 of the workshop, and I hope to see you back then. Bye.